In this video lab report, we will use fundamental physics principles along with data collected from observations on Earth to determine the mass of a black hole in space. Here's the experiment setup. A star with a known mass is observed on Earth. Its position is recorded every day or every 86,400 seconds. To give you an idea, here is the data from the first few observations. From this position data, we can observe the star's change in momentum over time and therefore determine the net force on the star. If we make the assumption that the only object exerting a force on the star is the invisible black hole, then we can use Newton's law of universal gravitation to make a good approximation of the mass of the black hole to be 3.3832 times 10 to the 31st kilograms. This is Newton's law of universal gravitation. To determine the mass of the black hole, we first need all the other pieces of the equation. We know the gravitational constant and the mass of our star. We also know the position of our black hole, and as mentioned earlier, we have position data for our star taken at regular time intervals, which we can analyze to find our final piece, the net force. To make these calculations manageable, we will do them in a VPython computer code. Here is the first part of the code, where we establish initial conditions. From two of these position data points, we can calculate the change in position over time, or the velocity, and from two of these velocity points, we can calculate the change in velocity. We will do this over and over again for all of our data. Remember, this is only the first few data points. The next step is to calculate the star's momentum at each time interval by multiplying the velocity by the star's mass, and the change in momentum by multiplying the change in velocity by the star's mass. We can now define this change in momentum over time as our net force. Remember, this is a fundamental principle called Newton's second law. You can see what this looks like in the code here. Now let's look at the net force in greater detail. We know that the perpendicular component of the net force describes changes in direction, and the parallel component of the net force describes the star speeding up or slowing down. Now we can define the parallel component as the magnitude of the change in momentum over time times the direction of our initial momentum. And we know by Newton's second law that this also equals the net force in the parallel direction. However, we don't have an easy way of calculating the perpendicular component of the change in momentum over time. However, we already know change in momentum over time and change in momentum over time parallel. So we can subtract these and get the change in momentum over time perpendicular, or F net perpendicular. Now that we have defined the parallel and perpendicular components of force, we can visualize the force better when we run the code. However, before we run the code, there is one final step. We need to define the net force and the distance between the star and the black hole as magnitudes, and then rewrite Newton's gravitational equation to solve for the mass of the black hole. Now we're ready to run our code. The program is now predicting the star's motion. On the left, it is calculating the mass of the black hole at every time interval. This visual prediction shows the star's motion is forming an ellipse. The blue arrow represents the perpendicular component of the force. It always points towards the center of the ellipse and grows in magnitude as the star experiences a sharper change in direction near the black hole. The black arrow represents the parallel component of force. Notice how the arrow is pointed in the direction of motion when the star is speeding up as it moves toward the black hole, and how it's pointing in the opposite direction of motion as the star slows down while it moves away from the black hole. You can see that now. The magnitude of the parallel component also changed as it traveled around the black hole, based on how fast it was speeding up or slowing down. The yellow arrow represents the net force and always points towards the object exerting the net force, or our black hole. The net force was also greatest in magnitude closer to the black hole. The mass of the black hole should have been consistent over each calculation, and you can see here that up to 5 significant figures it is. The mass of our black hole is 3.3832 times 10 to the 31st kilograms. To make an even more precise measurement, we could have made the time interval between the observations of the star's position even smaller. In conclusion, we can use fundamental physics principles, including Newton's second law and Newton's law of universal gravitation, along with observations of a star's motion as it interacts gravitationally with a black hole, to make a good approximation of the mass of a black hole. Let's discuss some brief questions. We've been saying that according to Newton's second law, F net is equal to dp dt. However, what are the differences between these quantities and their components? Well, F net is a physical quantity which causes changes in motion, while dp dt is a mathematical quantity that allows us to measure changes in motion based on observations of velocity and position data. The same is true for their components. For the second question, let's look at Newton's law of universal gravitation. We know that F net has to be the same because we got that from just motion about the star's location. So the only way that the mass of the black hole is different, let's say by a factor of x, is if the mass of the star is different by a factor of 1 over x. So if the mass of the star is the same, the mass of the black hole must be exactly the same.